This is Mrs. O'Neill for AP Chemistry, Chapter 11, Section 3, Select Properties of Liquids. You should have watched the introductory video. This is what I got from it. He talked about intermolecular forces, and again, those are the forces between molecules. And he talked about how there's 43 drops of water on this penny because of the hydrogen bonds, and the hydrogen bonds are strong IMFs between those water molecules. Gave you a nice flow chart as always. And again, he talked about intermolecular forces are like those yellow, the yellow rings, right? They're between the yellow lines or the yellow circles between those molecules, and the intra is the molecule itself. So like those blue circles, all of the bonds inside that molecule. So he talked about what happens as we take a certain strength. Let's say we have the strength right in the middle and we weaken it. Well, what's going to happen to those molecules? They're going to move farther apart. How about if we go the other way? Here we have, again, a strength, a certain strength in the middle. And what happens if we make it stronger? Then they get closer together. So I'm going to show you that one more time. So we start in the middle and we get weaker. Those molecules are going to move away from each other, and as you strengthen those intermolecular forces, kind of like a solid, right? Those molecules are coming together and becoming stronger like a solid. So then he talked about certain properties like melting and boiling points, and he said the greater the IMFs, the harder it is for those molecules to go from that solid to a liquid or the liquid to a gas. So that means that they're going to have a higher melting or boiling point. Surface tension is like the skin over a liquid. So if we look at down here, he was mentioning how you have three, let's say little beads or you know, little liquids. And he said how mercury, because it has the greatest IMF, it's going to form that circle. Water, on the other hand, is going to form like a bubble like it did on the penny. But if we took alcohol and we put it on, let's say, a piece of wood or on your countertop, it would just kind of slide all over the place because it's the weakest of all of these three IMFs. So again, as you get stronger, surface tension would be greater. Talked about capillary action, and this is just the action of liquid in a thin tube. And he talked about how water has cohesive attractions and adhesive attractions. So the cohesive is how much attraction it has for itself, and that's kind of why it dips down in the tube. And it also has attraction though of its container, and that's why it goes up the tube, and that's why water can go up a tree, and that's how they get so tall. Where mercury, however, only really has cohesion forces because it's only attracted to itself, and that's one of the reasons why when you look at these tubes, the mercury is actually curved down. So water is curved up because it's attracted to itself and the container, where mercury is only attracted to itself, not the container at all, so it's going to be curved in a different way. He talked about vapor pressure, and again, this is something we're going to get into more detail, but we want to remember, first of all, that vapor pressure is measured in a closed system. So nothing can get out, nothing can get in, right? So we kind of have to close that system. So a container has to be totally sealed, or the room has to be totally sealed. So we want to remember that here's our molecules in a liquid phase, and here's those molecules in the gas phase. So really at the surface where that liquid and gas meets, that's where a liquid becomes a gas, right? So the liquid's going to migrate, they're going to move all over the place, and once it reaches that surface, once that molecule or atom has a certain temperature, boom, it's going to go into the gas phase. So all of these gas phases, or all these gas molecules above the liquid, that's where the vapor pressure is. So we want to remember that the higher the vapor pressure, that means there's more volatile the liquid will be. In other words, volatility just means going from that liquid to gas phase. So the higher the vapor pressure will mean that that liquid is more volatile, which would mean that it is weaker. So we want to remember that as well. So the lower, the weaker the IMF, the higher the vapor pressure, right? If your molecules in your liquid phase are weak, it's going to be very easy for them to get to the gas phase. So the lower or the weaker the IMFs, the higher the vapor pressure, because more gas molecules will be up in that area. He also talked about basically like dissolves like. If you have a polar substance, it will dissolve a polar substance. If you have a nonpolar, it will dissolve a nonpolar. But water and oil do not mix because that is a polar and a nonpolar. Then he also talked about gases, which we talked again a little bit about this last chapter. The ideal gas is really an imaginary model, which it assumes no attraction between molecules and there's an infinite amount of space. We know that that really is not 100% true because as we cool down those gas molecules, it becomes more like a real gas and there is some kind of attraction to it, and we can see that there's a finite space between those gas molecules. He also talked about how in an ideal gas, this PV equals nRT, this ideal gas would be this blue line. It would always be 1, right? Think about that 1 atmosphere, right? That's where we kind of get our STP from. But a real gas, like the nitrogen lines, right, depending on the temperature, well, your pressure in your molecules are going to move slightly different. So the farther the line is away from that blue line, that standard line, the farther away that gas will be from an ideal gas. So he looked at hydrogen and nitrogen to give you an example. So again, which one is more likely going to be or act more like an ideal gas? And that would be hydrogen because it's closer to that standard line of an ideal gas. So hydrogen is going to be more like an ideal gas. And one of the reasons is because it has a smaller mass, a smaller molar mass. And he also talked a little bit about biological systems and how enzymes are like IMFs because they kind of have to fit inside each other like a lock and key. Onto your notes packet. Again, I suggest writing the notes, pausing the video, writing the notes, and then listen to hear my words. So in this section, you're going to learn that the nature and strength of intermolecular forces between molecules are responsible for properties such as viscosity and surface tension. Hot lava oozes and flows, scorching everything in its path, and occasionally overrunning nearby houses. When the lava cools, it solidifies into rock. The properties of liquids are related to IMFs. You will learn about some of the properties of liquids. So viscosity. Yet again, it's just how a liquid flows. So if you have large or strong IMF forces, the higher the viscosity. The higher the viscosity, we want to remember it's going to flow slower. Okay, so the more viscous something is, the more thicker it is, I don't know how else to say that, which means it probably has more complex molecule, which means it probably has a higher molar mass. So here's an example. Water, 18 grams per mole. Then we have syrup, a little thicker substance. I looked it up, it's about 180 grams per mole. Then we have something like oil. Now, oil and syrup to me kind of are similar, okay, as far as flow, but oil has a higher molar mass. And then we have something like honey, okay? And honey, you don't even pour honey. You use this funky little doodad to get the honey out. Well, what does that say? Well, your fast pouring is your low viscous substance, and your slow pouring is your high viscous stuff. And notice again the molar mass. So as we increase the molar mass, as we increase the complexity of that molecule, we are going to increase the viscosity, which means it's going to pour slower. Surface tension, like he said, is like a skin on the water, and it's just an inward force. Tends to minimize the surface area of that liquid. So here's an example as well. So here's our surface and here's our liquid molecules. So it's going to minimize that surface area by saying, look at this, the molecules at the top are really being pulled or are attracted to the molecules underneath, as well as the molecules in the middle are attracted by all sides. So that's how you kind of minimize that surface area. So when those water droplets are put on that penny, they kind of hold on to each other, and that's why they make that bubble. Okay, they're holding on to each other. So these guys are really holding on to each other, and on the surface, they're kind of getting pulled in. So imagine here on the sides, these guys would be pulling all of the molecules in towards them, like they don't want to fall over the penny. Surface tension makes it possible for some insects, such as this water strider, to walk on water. Water molecules at the surface of water drop above cannot form hydrogen bonds with the air molecules, so they are drawn into the body of the liquid, producing surface tension. Now, this is a 10-second video on a water bug that I actually took when we were at a party near a lake. So I thought that was pretty cool, and when I saw it, I said, AP Chem, and I had to record it. Capillary action, he also talked about this. Again, the rising of a liquid in a narrow tube. Cohesive versus adhesive. Cohesives are the intermolecular forces. He talked about how they are attracted to themselves, and adhesive forces are the attraction to the container that it's in or to something else. So again, adhesive forces, as we increase or as the glass is polar and the water is polar, there's going to be an attraction, and we're going to have both adhesive and cohesive forces, and that's why we have that dip in the liquid. Okay, so that's where that meniscus comes from. So this is a nice picture. You might want to pause and kind of look it over, but again, we explain how there is the dip for the water, but in mercury it's the other way around, and that's because in water you have the adhesive forces are greater than the cohesive, versus in mercury your cohesive are greater than adhesive, right? So here your adhesive, the attraction to the glass is greater, where in mercury the mercury molecules are more attracted to themselves than they are to the container. So that's what happens there. Beading, again, more like surface area or surface tension. So a polar substance is placed on a non-polar substance. This causes more cohesive forces causing this beading. And that's really what happens with that lotus plant. That lotus plant and the water that forms on it, there's beading, and this is why, because of the polar versus non-polar effects. See you in class.